Hi, welcome back to Mrs. Ogram's Maths. This is the worked solution video for the Level 3 Calculus paper from 2023 for 91578, which is the differentiation external. One important thing to note is I'm making this video before the mark scheme is actually available. Whilst I've done my best to check all the work in every way I could think possible, there might still be some errors, and if I do discover errors, I will pop them into the video description. If you find them while watching, please add a comment and I will look into it. Thank you. For question 1, I'm going to start by rewriting this in powers. So a square root would be to the power of a half. That makes it a bit easier for me to see the differentiation. So that will now be chain rule, and it's a half 3x minus 2 to the minus a half times by the derivative of the inside, which is 3. You don't need to simplify it, but you could also write that as 3 over 2, 3x minus 2 to the minus a half. And you could also write it as 3 over 2 root 3x minus 2. Any of those would be accepted. For b, we're finding the rate of change of this function, so we need to differentiate our function of t. Now we have a product rule happening here. We've got one bit times by another bit. So we will first of all differentiate the first bit, that's 2t, and times it by the derivative of the second bit, which is e to the 2t, and then leave the first bit alone and times it by the derivative of the second bit, which is 2e to the 2t. Then we're finding what that is when t is equal to 1.5. So 2 times 1.5 is 3, times it by e to the power of, again, 2 times 1.5 is 3. Then we'll add on 1.5 squared times 2 times e to the power of 2 times 1.5, which is 3. We get to 150.64. For part C, we are given this diagram with the equation for the curve is 2 over x plus 1 to the power of 3. We know that the second tangent to this curve is drawn that's parallel to this first one here. So let's think about where that would go. Grab your ruler and you can sort of get it so that it's parallel to this one, roughly speaking, doesn't have to be perfect. And then it just touches the curve somewhere else. So it's going to be just about here. So I'll draw that line in like this. Okay. So that's the line that we're thinking about now. And we want to find the x-coordinate of the point where this second tangent touches the curve. So we're looking for the coordinate just here. Okay, first I will rewrite the y equation in power form. We know we're going to need to do some differentiation with it, so that is easier for me to deal with. Now, the gradients are going to match for both of these two lines. So let's find out what the gradient equation is first. So this is chain rule. Bring the 3 down. We've got minus 3 times 2 is minus 6. Reduce the power by 1. And times by the derivative of the inside, which in this case is just a 1, so we don't really need it. Now we're told in the question that this first tangent is happening when x equals 1. So this right here is happening at x equals 1 there. And our second tangent will match that gradient. So when x equals 1, dy by dx will be equal to minus 6 over 1 plus 1 to the power of 4. Now, 1 plus 1 obviously is 2. 2 to the power of 4 is 16. So this is the same as minus 6 over 16. Or if we want to simplify that, that's going to be minus 3 over 8. So we want to find the other place where our gradient function is equal to minus 3 over 8. We know that it happens in two different places because we have these two different lines where the gradient is the same. So these matching lines here, that purple line, our second gradient that we're looking for, will also have this gradient of -3/8 because it matches this line just here. So solving this now, if we bring the 8 up to the left-hand side, we can multiply, we can get rid of the negatives too. So we've got 48, and then bring the x plus 1 up to the power of 4 up to the right-hand side. So now if I divide both sides by 3, I'll have x plus 1 to the power of 4 is equal to 16. The fourth root of 16 is 2, so if we do the fourth root of both sides, we get that x plus 1 equals 2. It's actually plus or minus 2, my apologies there. Just the same as when you square root things, you need to consider the possible negatives as well. So then x could be 1 plus 2, or x equals, minus 1 plus 2, or x equals -1 minus 2. So this gives me x plus -1 plus 2 is 1. This one is -1 minus 2, which is -3. Now, going back to our graph, we've got the x equals 1 here. So the coordinate that we were looking for, it must actually be on this -3. So x equals -3 for the second tangent. So let's just pop that all onto one screen so you can see the whole thing all together before we move on. Okay, now let's move on to D. Now this one is one of those questions that you might not figure out what exactly you're aiming for when you first start off. So just take some clues from the question, which is that we have parametric equations, and we got the two equations for x and y. And so start this one by trying to work out dy by dx. So we need to do dx by d theta first. Now if we differentiate 4 cos theta, we get -4 sine theta. And dy by d theta, if you were to differentiate 4 sine theta, then you get 4 cos theta. So then from that one, dy by dx is equal to 4 cos theta over -4 sine theta. That's just using parametric equations. The next step here is to work out what we can substitute in for cos theta and sine theta in terms of P and Q. Because we have this tangent here that runs through that point P and Q, we know it will include this point P and Q and have this gradient here. So think about it as trying to find the equation of the line. But before we can substitute things in, we need to have things in terms of cos theta and sine theta, because at the moment it's not in P's and Q's. Have a look at this. Actually, let's just change that up. We'll do this green triangle here, and thinking about this being our theta angle, then the x distance there is P and the y distance here is Q. So then at the point P, we have x equals P and y equals Q. Now going back to our parametric equations, x is equal to 4 cos theta, y is equal to 4 sine theta. So P is equal to 4 cos theta and Q is equal to 4 sine theta. Now that means we can express cos theta in terms of P, so that's P over 4, and sine theta is equal to Q over 4. Now going back to our dy by dx, we can now substitute in some values that turns our cos thetas into and sine theta into P's and Q things. So back to this here, we'll have 4 times cos theta, which is P over 4, divided by -4 times sine theta, which is Q over 4. The 4's cancel, and we're left with minus p over q. So now we've got a gradient. We also have a point on the curve, which means we can find the equation of the line using y minus y1 equals mx minus x1. So the y coordinate is q. The gradient is minus p over q that we just did here. And the x coordinate is p. So we have, if we multiply that through by q, we'll have qy minus q squared equals minus p. Also expand this right bracket, we'll have minus px plus p squared. And that we can rearrange, bring the px over to the left-hand side, plus qy, take the q squared over to the right-hand side, and we've got px plus qy equals p squared plus q, which was what we were looking for in the question. All right, part E. Quite a lot of information being given to us here, so if you haven't already read this through, have a pause and read. I'm going to start by saying let T be the area of the triangle. So this area here, we're going to call it T. I'm avoiding A because we've already got an A being used here for this area. Now we're looking to find the maximum area of that triangle. So what we want is dt by dx so that we can set it equal to 0 to maximize it. Okay, so that's what we're aiming for. So let's start by thinking about how do we find the area of that triangle. It will be half times the base times the height. So this will be half. Well, the base is the x coordinate, wherever we get to along here. The height will be to find the y value at that x point. And to find y, we've got the equation up here. So that will be to multiply by x minus 2m squared. So this is half x squared x minus 2m all squared. So now if we're to do dt by dx, we're differentiating that. We have product rule, so I'm doing this bit differentiated and then times this bit and then reverse that for the process for doing product rule. So the first bit differentiated, half x squared becomes just x times by the bracket part. We haven't changed that, so that stays as x minus 2m squared. Then leave the first bit as it is and times by the derivative of the second bit, which will be 2x minus 2m. It would be times by the 1 because that's the derivative of the inside and we're doing chain rule, but obviously we don't need to do a times by 1, write it out. Okay, so now we set this equal to 0 to be able to find a maximum. So we have x minus 2m squared plus x squared x minus 2m squared. Oh, whoops, sorry, 2m, I put the squared in the wrong place there. There we go, is equal to 0. Taking out some factors here to solve this through, we can take an x out of everything. We can also take an x minus 2m out of all of those terms. So this first term here, I'd need another x minus 2m. And this term here, I'd need another x. Okay, so from these solutions, this one would give me x equals 0. This one would give me x equals 2m. And this one would give me 2x minus 2m is equal to 0. So 2x equals 2m, or x equals m. Now let's consider each of those solutions. If x was 0, let's just go back here. If x was 0, we'd be just here. that x value is not going to give us a maximum. It would give us a minimum. Similarly, if x was 2m, we would be up here, and that's going to be a minimum, not a maximum. So those first two won't give a maximum. So we carry on with this x equals m being our solution. So the maximum happens when x equals m. Now let's think about how we do this last bit. We want to show that that maximum is 3/8 of the total shaded area. So let's pop that into the formula for finding the area of the triangle. So when x equals m, we have the area of the triangle going back to what we found out up here. So this bit just here, that's our area of the triangle. So this will be half times m squared, m minus 2m, just putting m in place of the x that was up there. Okay. So then working that through, we have half m squared times minus m all squared. So minus m squared is just going to be m squared, and that is m to the 4 over 2. Now back to what we were trying to work out, which is this part here. The A area is 4m to the 4 over 3. We want to show that this result we just got is 3/8 of that. So if we go to 3/8, just a sec. So 3/8 times the area of A is equal to 3/8 times 4 over 3 of m to the 4. Now 3/8 times by 4 over 3 is equal to a half m to the 4, which is equal to what we just showed there. Or we can rewrite that as m to the 4 just to make the point. Oh, sorry, m to the 4 over 2, the area of the triangle, or the maximum area of the triangle. Okay, so for this one, we are finding the derivative of f of x. Now we have a quotient rule because we got something divided by something else. So we do v du by dx, so that's the bottom times by the derivative of the top, minus u dv by dx, top, times the derivative of the bottom, which is minus sine x, all over the bottom squared. Now you can leave it like that, but if you want to tidy it up, it would look like this. Okay, on to B. So first of all, we need the gradient of the curve. So we need dy by dx. If we differentiate cot, we get minus cosec. So minus cosec squared of the thing that was inside. Now, because we've got a 2x inside, we're using the chain rule, so we need to multiply by 2. Now, when x is equal to pi by 12, y would be equal to minus 2. Cosec is sine, 1 over sine. So this will be sine of 2x, and then the whole thing gets squared. So pop that into the calculator. We'll be doing minus 2 divided by sine of 2 times pi divided by 12. And that thing will be squared. We get an answer of minus 8. Okay, for part C, we have this equation here. We want the x coordinates where the tangent is parallel to the x-axis. So tangent parallel to the x-axis means that the gradient dy by dx will be equal to 0 to make it a horizontal line. So in this one, we've got another quotient rule. We've got something over something else. So if we take v du by dx, we will have ex times x squared plus 2x. So our v bit times by the derivative of the top, which is just e to the x, minus u dv by dx, so e to the x times by the derivative of the bottom, all over the bottom squared. So x squared plus 2x squared, and we'll set that equal to 0. So now we're only interested in the numerator being equal to 0, since if we bring that denominator up and multiply it on the other side, that's going to turn to 0. So on the top, we have ex, x squared plus 2x minus 2x plus 2 if we take out a factor of e to the x. So this 2x and minus 2x cancels there, and we end up with x squared minus 2 inside that bracket. But before that, we'll say this can't be 0, so x squared minus 2 must be 0, so x squared is equal to 2, and x has to be plus or minus root 2. Now for D, we want to find the points of inflection on this graph here. Now points of inflection happen when the second derivative is equal to 0. So let's step through to get to that point. First derivative will be, this is the product rule. So we have a piece here being multiplied by a piece here. So we need to do a product rule on that. So we'll do 3x squared times by 1 over x plus 6x times log of x, and that simplifies to being 3x plus 6x natural log of x. Now if we do the second derivative, we need to differentiate that one. So 3x differentiates to 3. We have another product rule where we've got one piece times by another piece. So we do product rule on that one as well. So if I differentiate 6x, I get 6. And then if I differentiate log x, I get 1 over x. So then we have this here will cancel to just being 6. So 3 plus 6 is 9 plus the 6 log x. Now for a point of inflection, that is set to be equal to 0. So 6 log x is equal to minus 9. Log x is minus 9 over 6. So x is equal to e to the minus 9 over 6, which we can do over here. E to the power of negative 9 over 6 is going to be 0.223. Okay, now for the excellence. This was a particularly tricky one. So the pieces in the question we need to pay attention to. We've got the helicopter is flying at a constant speed of 72. It's 100 above the ground, and that doesn't change, so we can just look at that as being a fixed, 400, not 100. Then we have that the direct distance from the helicopter to the car is 2,500. So that's not a fixed amount, but it's 2,500 meters when this next bit is true, which is that the angle theta is increasing at a rate of 0.002. So when d theta by dt equals 0.002. I'm just going to add a little bit to the diagram. That helicopter is going at 72 meters per second. Okay, now if this angle here is theta, this angle here is also theta. We might want to use that a bit later. And I'm going to call this distance here x. So the distance along the road between where the helicopter is and where the car is, that is x. Now the thing we want to work out is the speed of the car. So that's my starting point. This is a related rates of change question, and I always start by writing down the thing that I want to work out and see how I can relate it to the thing that I know. So I know d theta by dt. If I need to turn that into dx by dt, I would need to times that by dx by d theta, which is a little tricky to spot how to get that out of what we have. But what we can see is we've got a right-angled triangle that involves x and theta. So if I'm looking at x, I've got the opposite here, the adjacent and the angle. So that's to do with tan. Now to find the adjacent, I will do the opposite, which is 400 divided by tan theta. Or in other words, 400 and then tan theta to the minus 1. Now that I've got it in that form, I can do dx by d theta. So if I'm to differentiate that thing, differentiate the outside, it's a chain rule, reduce the power by 1 here, so that's a minus 2, and times by the derivative on the inside, which is sec squared theta. So tan theta becomes sec squared theta. Now let's try to do some simplifying. We have minus 400 over tan squared theta. Sec squared is 1 over cos squared. So this is minus 400. Tan is sine over cos, so this is sine squared. Oh, but because it was 1 over, it gets flipped, so it's cos squared over sine squared times 1 over cos squared. So now you can see the coses cancel, and we have minus 400 over sine squared theta. Okay, just so I can fit it all onto one page, normally I would go on and use a bit more space. We actually have an entire page that's available to us, but I want to try and keep this compact for the sake of the video. So from here, I'm going to take that information and go back to what we're doing over here. Okay, so dx by d theta, dx by dt uses d theta by dt, which was the 0.002 we were given in the question. So we were told that we have that information there. And we're going to times it by dx by d theta. So this will get multiplied by minus 400 over sine squared theta. Now the next stage, we don't have a value of theta to put into this from the information that we've got in the question. We need to find something that can help us to work out theta. What we do have is this 2,500 meters at this particular point. So we can use that to work out something for theta. So now sine theta is going to be 400 over 2,500, just by using trigonometry on this. We've got the opposite and the hypotenuse. So sine of theta is opposite divided by hypotenuse. That's what I've got just down there in the blue. Now I can take that sine theta and put it in for sine squared theta. So dx by dt will be 0.02 times minus 400 over sine squared of, where sine squared is equal to 400 divided by 2,500. So that's 0.16. Let me just pop that in there. That was equal to 0.16. So on the bottom here would be 0.16 squared. What I'm doing is substituting into this bit what the value of sine theta was. Okay, so now if we take that, we're going to square it. We'll do 400 divided by it, and then we'll do 0.02 times the negative of our answer. Oh, that's not quite right. Hold on just 1 minute. I've missed, oh, there it is. I've missed a 0 in here. Let's go again. 0.002 times by negative 400 divided by 0.16 squared gives me minus 31.25 meters per second. Now we're not quite finished there, and the minus should give you the idea that we're not finished because the car can't be doing a negative speed. What that dx by dt is telling us, go back to the picture, remember our helicopter is already going at a speed of 72. And it's trying to catch up to the car. So we're hoping that it's closing the distance. So this distance x is not the speed of the car, it's not the distance the car has been, it's the gap between the helicopter and the car. So this rate of change is telling us how fast that gap is closing down. So if the helicopter is already doing 72, that gap is closing at a rate of 31.25, so the car is going that much slower than the helicopter. So if we take 72 and we subtract the 31.25, we have a car speed of 40.75 meters per second. Question 3, we are going to differentiate this natural log. To do that, the derivative becomes the thing inside of the log goes on the bottom of the fraction, and then on the top we have the derivative of what was inside of the log. So it looks like this. And that is the chain rule using the derivative of the natural log being 1 over x and then times by the derivative of the inside. Okay, we have a picture, some stuff going on with this function, and we need to determine these things in the question. So we want to find the values of x where f of x is continuous but not differentiable. So continuous means you can draw it without taking your pen off the paper. So if we were to draw all the way along here, we'd have it's not continuous at these points where we have holes or we have a complete break in the graph. Now anywhere where it's smooth, we can differentiate that, we could find the gradient of that, but we can't do it where there's a kink in the graph like this one here. So that's the only place where there's a kink, but we don't need to take our pen off the paper to be able to draw it. So that's when x equals 8. The second part, the values of f of x where f dash of x is 0. So this means it's a stationary point. And f double dash of x is less than 0. So it's a stationary point when we are in a maximum. So we're looking for maximum stationary point. And that happens just here at x equals minus 4. Now the limit of this function as we approach as we approach 6 is we look at what's happening if we go towards 6 on our graph from the right and the left, what's happening on the graph itself. So if we head towards that from the right, we're heading towards a value of 5. If we head towards it from the left, we're heading towards a value of 2. Those two things have to match for there to be a limit, so therefore the limit does not exist. Right, now we have part C. And we've been given parametric equations. From there, we need to find the gradient of the normal to the curve. So we'll need the gradient of the curve itself first. And for that, we need to do dx by dt and dy by dt. So let's start with the x. If we were to differentiate this here, we will end up with bringing the pi by 5 outside of the bracket for chain rule. then times by 5 root 2. Sine turns into cos when we differentiate it, and then we have the inside of that function. Now, dy by dt, so we're doing this function now. Well, the 10 differentiates to 0. The minus 5 root 2, cos turns into minus sine, so it will cancel out the plus that the minus that we have there into being a plus. But we will also bring out the 5 over pi that we get from differentiating the inside. So we end up with, oh, I missed the 5 root 2, and then sine of pi t by 5. So then dy by dx is to take the dy part. Now that 5's going to cancel in both of those, so we can cancel that off. We've got pi root 2 sine of pi t by 5 all over the x part, so that is pi root 2 cos pi t over 5. Now the pi root 2 cancels on the top and the bottom. Sine over cos is tan, so this is tan of pi t over 5. So when t is equal to 6.25, dy by dx is equal to tan of 6.25 pi by 5. So over to our calculator. Here we go. 5. So tan is 1. So then the gradient of the normal, just to finish this off, if the gradient of the tangent is 1, gradient of the normal is equal to minus 1, negative reciprocal. Part D, we are finding the coordinates of any stationary points and then identifying their nature. So let's start by finding them. So f dash of x is equal to, well, actually let's start with f of x and write it in powers form first. So this is x to the minus 1 minus 2x to the minus 3. So f dash of x is equal minus x to the minus 2 plus 6x to the minus 4. And for stationary points, we need to set that equal to 0. Now that's 1 over x squared. This is 6 over x to the 4. And solving for that equal to 0, we can take out a factor of 1 over x squared from both of these. This will be a minus 1. This will be a plus a 6 over x squared is 0. So either this is equal to 0, but that's not valid for this equation because we can't divide by zeros on the bottom here. Okay, so that's not valid. So therefore, minus 1 equals 6. Oh, sorry, minus 1 plus 6 over x squared equals 0. So 6 over x squared is equal to 1. Or x squared equals 6, so x is equal to plus or minus root 6. Okay, so there's the 2 points for our stationary points. Now we need to, we need the full coordinate. Okay, so we'll need the y value as well, and then we need to identify the nature of them. So let's set up what the second derivative will be to get, so we can use that for the nature of the points. So from this bit that we have up here of f dash of x, I'm going to differentiate that piece again. We will have 2x to the minus 3 minus 24x to the minus 5, or 2 over x cubed minus 24 over x to the 5. Okay, when x equals root 6, y equals, we have our equation up here for f of x, so 1 over x minus 2 over x cubed. So 1 over root 6 minus 2 over root 6 cubed. And f double dash of x will be 2 divided by square root of 6 cubed minus 24 divided by square root of 6, and that's to the power of 5. I'm just substituting into my f double dash of x over here, which is minus 0.136. It's less than 0. So that gives me a point that's root 6, 1 over root 6 minus, in fact, we probably should just do that as a decimal now. So 1 divided by root 6 minus 2 divided by, it's going to be 6 root 6 if you cube that. So that's 0.272 is a maximum because the second derivative was less than 0. Now let's try out the other x coordinate. So when x is minus root 6, y equals 1 over minus root 6 minus 2 over minus root 6 cubed, and f double dash of x is to go back into what we just had here, and oh no, we'll need to start again. So 2 divided by negative root 6, and that's to the power of 3. I'm just going to put a bracket around those just to make sure. Okay, and then taking off 24 divided by negative root 6 to the power of 5. Again, I'm just substituting into the second derivative there, and I've made a mistake somewhere along the lines. So let's just check what I've got in here. In fact, I'll just start again. We got 2 divided by the square root of, or rather the negative square root of 6. And that was put to the power of 3. And we're going to take off 24 divided by the negative square root of 6 put to the power of 5. And that gives me 0.136, which is greater than 0. So root 6. What we've had on this one, which I've just noticed a small error, I put the minus in twice. On this bit here, this should just be negative 1 over root 6. Okay, so let's go with minus 1 divided by root 6. Take away 2 divided by root 6. And that bit got cubed. And also I missed a minus. Gets me a negative 0.27. And that is a minimum because this double dash of x was greater than 0. Okay, we got there in the end. That was a slightly painful one. Right, the last one of these excellences now. We have this equation for a cable. We want to use differentiation to verify that we can get this form out of it. Okay, so let's start by, if we begin with this, what we need to work out is what's dy by dx, what's the second derivative, and then see if it can make this all together. Okay, so if y is a over 2 e to the, I'm going to rewrite that as 1 over ax, and then e to the minus 1 over ax, because I find that easier to deal with the derivative then. Then we will get dy by dx is equal to, from this first term here, the e part doesn't change, but we do multiply by the derivative of the x. So we will have a over 2 times by 1 over a. So the a's cancel and we just have a half. Okay, then the second one, remembering that we're multiplying across here, so we have e to the minus 1 over ax, a over 2, times by negative 1 over a from bringing in that derivative there. So we end up with minus a half. Okay, from there we can get the second derivative. Okay, so this first term, again, e to the 1 over ax, the half gets multiplied by 1 over a, so we've got 1 over 2a, minus e to the minus 1 over ax, the half gets times by minus 1 over a, so that becomes plus 1 over 2a. I'll just rewrite that to make it really clear. So that's a minus 1 over a there. Okay, now looking at what we needed to do here, if we take the second derivative and times it by a, then a times d2y dx squared equals 1/2 e to the 1 over ax plus 1/2 e to the minus 1 over ax. That a multiplying through just cancelled those a's that are on the bottom here. Now, if we were to square this, because remember I'm trying to get back to showing this thing up here, so if I was to square that side, I'm going to see if I can make it equal to 1 plus dy by dx squared. Okay, so if I square that, it's the same as if I multiply by that bracket again, so I'm going to write it out just to make sure we don't miss anything. Okay, so first term, this one to this one, is going to give me 1/4 e to the, now if we're timesing things with powers, those powers get added, so 1 over a plus 1 over a is 2 over ax. Okay, then we have this one times this one, so we have 1/4 e to the, now again we're adding the powers, so the minus 1 over a plus 1 over a cancels out, and that's going to be e to the 0. Next we will do this one times by this one, so we have 1/4, hang on, plus 1/4 e to the, again we've got plus 1 over ax and a minus 1 over ax, so that will be to the 0, plus the final piece, this one times this one, which will be 1/4 e to the minus 1 over a minus 1 over a is minus 2 over ax. Okay, now e to the 0 is just 1. So we have 1/4 plus 1/4. So this is equal to 1/4 plus 1/4 makes a half. Then we have 1/4 e to the 2 over a plus 1/4 e to the minus 2 over ax. Okay, now let's look at the right hand side. 1 plus dy by dx squared. That's what we had in the question up here on the right. That's inside of the square root, but remember I squared this piece. Okay, so dy by dx is just up there. So we're doing 1 plus a half e to the 1 over ax minus a half e to the minus 1 over ax. That's going to be squared, so times it by itself. And then we go through another similar process of multiplying out that bracket. So we have 1 plus. Okay, first term is going to be a quarter e to the 2 over ax minus a quarter e to the 0, where these two things multiplying together, the powers become 0. Then we have another one of those when we do this, those outside ones multiplied together. And then the final term, those end terms being multiplied together, gives me a plus 1/4 e to the minus 2 over ax. Okay, e to the 0 is 1 again, so this is 1/4, minus a quarter, and we have the 1 at the beginning. So 1 take away a quarter is half, and then we're left with a quarter e to the 2 over ax, and a quarter e to the minus 2 over ax. Oops, put the ax just there. Now let's just label this. Here's equation 1, here's equation 2, and you can see that they are equal. So 1 equals 2. Therefore, a times d2y over dx squared is equal to the square root of 1 plus dy by dx, all squared. And there you go. Some fairly lengthy algebra on that last one, but not especially difficult, just lots to do. And that is the integration paper complete. If you do find mistakes along the way, it's because I've been making this video before the mark scheme is available, and you are more than welcome to pop a comment onto the video to let me know if something needs correcting, and I'll be happy to do so. If you're watching this back later, just check the description for the video and any corrections needed will be in there. Thank you very much.